picture this. You've just integrated a cutting-edge AI assistant right into your development environment. You point it at a massive, completely undocumented, like 10-year-old legacy code base.
Oh, that sounds like a disaster waiting to happen.
Right. And you give it a seemingly simple prompt like, refactor the authentication module to use the new security library. You sit back, take a sip of your coffee, just watch the terminal.
Let me guess. It starts off fine.
Yeah, at first it looks great. The agent is searching files, doing its thing. But then it tries to run a shell command.
Yeah.
And it just hangs.
Yep. The classic trap.
The agent panics, right.
Yeah.
It tries to fix the error by executing this blanket text replacement, and suddenly you are watching an absolute horror as it accidentally overwrites a critical database configuration file.
Ouch.
Your whole system is broken, and your context window is just maxed out with error logs. So, welcome to a highly technical architect-level deep dive. Today we are exploring exactly how to prevent that nightmare.
It is a scenario that plays out far too often when developers first start building autonomous systems. They assume raw intelligence is just enough, but it really isn't.
No, it's not.
Yeah.
Which brings us to our mission for this deep dive. We are unpacking Scenario 4, Developer Productivity with Claude, and we are doing this with one absolute, uncompromising law.
The exam guide.
Exactly. For everything we discussed today, the official Anthropic examguide.md is our definitive absolute source of truth. Every architectural decision, every tool selection, every fallback mechanism we cover is strictly defined by that syllabus.
Absolutely.
We're focusing on hands-on, developer-centric principles for architecting flawless agentic systems. If it contradicts the exam guide, well, we simply aren't doing it.
And if we connect this to the bigger picture, building a developer productivity agent isn't just about handing a large language model a terminal prompt and, wishing it luck. It is a rigorous exercise in extreme resource management.
Resource management, I like that.
Yeah, we are dealing with context preservation, preventing hallucination, and enforcing strict boundaries on how an agent is allowed to manipulate a file system. Because if an agent operates without these constraints, it will succumb to token exhaustion and logic failures almost immediately.
I love how you frame that. It's not just about the code it writes. It's about how it behaves while it thinks. So let's start at the foundation, right? How the agent actually interacts with your files. The exam guide lays out a very strict built-in tool hierarchy.
It does, and the overarching philosophy here is structured predictability. The absolute golden rule of this hierarchy is that the agent must prioritize dedicated built-in tools over arbitrary bash commands every single time.
Okay, let's unpack this, because there are 6 specific built-in tools defined in the architecture: Glob, Grep, read, edit, write, and bash. Now, speaking as an engineer, my instinct is immediately screaming, why do I need 6
Or you just want to jump into the terminal.
Exactly. If I need to find a file or change a configuration, my muscle memory just types a bash find or a grep or a sed command right into the terminal. Why is the exam guide so hostile to just letting the agent run bash?
Because you are a human, and you possess intuition that a language model simply does not have. When you run a bash command, you can visually parse the chaotic output on your screen.
Sure.
You know how to handle an interactive prompt if the command suddenly asks for a yes or no confirmation. You understand what it means when a command returns, like a cryptic standard error. A language model relies on structured contracts.
Oh, okay.
Built-in tools provide a predictable JSON schema. The model knows exactly which parameters are required, and more importantly, the tool guarantees a cleanly formatted, predictable response.
I see. A shell environment is just too wild for it. If a bash command hangs, the agent just sits there burning tokens, or worse, hallucinating that it actually succeeded.
Precisely. Arbitrary bash commands operate in a highly variable environment. Dependencies might be missing, environment variables might be wrong, or the output might be thousands of lines of unstructured text that instantly floods the context window.
Which is a nightmare.
Yeah. The exam guide strictly dictates that bash is the tool of absolute last resort. You only use it when no specialized built-in tool can possibly do the job.
That makes a lot of sense. Predictability equals safety. So if bash is mostly off the table, let's walk through what the agent should be doing. We have Glob and Grep for searching. How does the architecture differentiate between them?
It separates them by their specific target. Glob is exclusively your pathfinder. Its sole purpose is to locate files by their name or by an extension pattern.
Okay, so like a wildcard search.
Exactly. Let's say the agent needs to find every unit test in a massive React project. It uses Glob with a pattern like, ****.test.tsx. That is it. Glob answers one question: where do these files live? It does not look at the code inside them.
Which is where Grep comes in.
Exactly right. If you need to search the actual contents of the files, you use Grep. So if the agent needs to figure out where a specific database connection function is being called, or locate every file that imports a deprecated logging module, Grep scans the contents across the code base efficiently.
Okay, I'm tracking. Glob finds the files. Grep searches the text inside them. What happens when the agent actually needs to look at the whole file?
Then it uses the read tool. But there is a very common trap here that the exam explicitly warns about.
Oh, what's the trap?
The read tool is only for loading the full contents of a specific known file path. The agent must already know the exact address of the file before calling read. You never use read to blindly scan directories or to open dozens of files just to look for a specific string.
Because opening dozens of entire files would just obliterate the context limit of the model.
Completely. It would overwhelm the model's attention mechanism with completely irrelevant code.
So we found the code, and we've read it safely. Now the agent needs to change it. We have edit and write. How do we choose between those two?
Think of edit as a surgical scalpel and write as a sledgehammer.
I like that analogy.
Yeah, edit is designed for targeted, precise modifications based on unique text matching. You provide it an old string parameter, which is the exact block of text you want to change, and a new string parameter. It finds that specific block and swaps it.
And the sledgehammer?
Write, conversely, is used when you need to create a brand new file from scratch, or when you are executing a 100% top-to-bottom overwrite of an existing file.
I can see how edit is safer, but I can also see how it could fail spectacularly. Let me throw a scenario at you.
Sure, go for it.
Let's say the agent is trying to fix a bug in a massive JavaScript file. It decides it needs to change a line that says return false to return true. Use the edit tool and passes return false as the old string. But, I mean, that line of code probably appears 20 times in a 1,000-line file. How does the tool know which one to change?
It doesn't.
Yeah.
That is entirely by design. If the old string parameter is not 100% unique within that specific file, the edit tool will hard fail and throw a match not unique error. It just refuses to guess.
Wow, that is a great safety feature. But it leaves the agent kind of stuck. If it fails, what is the recovery mechanism? Does it just give up?
No, not at all. The exam guide defines a very strict multi-step fallback algorithm for this exact error, and the order of operations here is critical.
Walk me through it. The edit tool just threw a match, not unique error. What is the agent's immediate next move?
Step 1. The agent must use the read tool on that file. It needs to pull the full current contents of the file into its context so it can actually see the surrounding code.
Okay, so now it's looking at the whole file. What is it looking for?
Contextual anchors. That is step 2. The agent analyzes the lines of code immediately above and below the target line. It is looking for enough surrounding text to make the target block unique.
Oh, I see. So instead of just trying to replace return false, it looks up and sees that the specific return statement is inside an if user.isLocked block.
Exactly, which leads directly to step 3. The agent expands the old string parameter in the edit tool. It includes the if statement, the return statement, and maybe the closing bracket.
Got it.
By expanding the block of text it wants to replace, it transforms a generic string into a mathematically unique string within that file. It then retries the edit tool with this expanded context.
That is brilliant. It essentially forces the model to be hyper-specific about where it is operating. But wait, what if it still fails? What if the file is just incredibly repetitive, like a massive JSON config file where the exact same block repeats 50 times?
Then we reach the absolute last resort, which is step 4. Only after the expanded edit retry fails is the agent permitted to fall back to a read plus write operation.
Meaning it reads the whole file, uses its own internal logic to manipulate the string within its context window, and then uses the write tool to overwrite the entire file top to bottom.
Correct. But notice how much friction the architecture puts in front of a full file overwrite. It forces the agent to try surgical methods twice before allowing the sledgehammer.
I have to ask, though, if a string isn't unique, why couldn't the agent just drop into bash and run a sed command to replace, say, the third instance of return false?
Yeah.
I mean, sed is literally built for text substitution.
And this is exactly the kind of human developer instinct the exam wants to train out of you.
Really? Why?
Think about how a language model operates. If an LLM writes a sed command to replace a string, sed operates blindly. If the agent makes a slight mistake in its regular expression, sed might replace every instance of that string in the file, silently destroying the logic of the application.
Oh, man. Yeah, that would be bad.
The built-in edit tool, with its uniqueness requirement, provides a cryptographic level guarantee that the agent is only modifying the exact logical block it intends to. It trades a tiny bit of latency for absolute structural safety.
Precision over raw speed. That makes perfect sense. Okay, so we've established how to safely modify a file. But let's zoom out a bit. Imagine we drop this agent into a 200,000-line enterprise application.
A beast of a code base.
Exactly. Before it can even use the edit tool, it has to actually figure out what to edit. It has to trace dependencies, find wrapper functions, and understand the flow of data. How does it investigate a massive system without instantly blowing out its memory?
It requires a highly disciplined, incremental investigation strategy. And to really understand the strategy, you first have to understand the primary anti-pattern the exam warns against.
Which is what? What's the trap here?
Using Glob to find every single file in a directory, and then aggressively looping the read tool to open every single file just to look for a specific function name or variable.
Oh, wow. I mean, I can see why an AI might try that. It thinks, I need to find this function. I'll just read every file until I spot it. But that sounds disastrous for the context window.
It is guaranteed context exhaustion. Large language models suffer from a phenomenon known as the lost-in-the-middle problem.
Right, where they forget the middle of prompt.
Exactly. If you force the model to ingest 40,000 lines of irrelevant code just to find 3 usages of a function, not only do you burn through your token limit, but the model's attention mechanism gets diluted. It starts forgetting the instructions you gave it at the very beginning because it's just drowning in irrelevant syntax.
It's like following a trail of breadcrumbs. You don't eat the whole bakery to find a single recipe. You just follow the specific path you need. So, to you listening, this is entirely about protecting the context window. What is the exact exam-approved sequence for tracing a dependency path without eating the bakery?
The exam outlines a strict 4-step incremental flow. Step 1. You always start with Grep. Let's say you were looking for an old authentication function. You use Grep to search the codebase for that specific function name. Grep returns only the matching lines on the file paths. It is highly efficient.
It gives you the entry points without loading the whole file.
Right. Then step 2. Now that you have the exact file paths from Grep, you use the read tool on only those specific files. You load them into context to look at how the function is implemented and to follow its internal imports.
Okay, so the agent reads the file and realizes, this authentication function is actually being wrapped by a higher-level security module.
Exactly. Which brings us to step 3. The agent drops the current file and uses Grep again. This time, it searches the codebase for usages of that new wrapper module.
And finally, step 4, it uses read on the consumer files that Grep just found. Grep, read, read. It's a targeted surgical strike. At any given moment, the agent only holds the exact files relevant to the current step of the trace in its active memory.
But here's the architectural challenge with that. Even with a perfectly disciplined incremental strategy, exploring a massive code base generates an enormous amount of intermediate data.
Right. If you are executing a major architectural refactor, like migrating a core database library across 50 different files, the agent is going to have to run dozens of Grep searches, read dozens of files, hit dead ends, backtrack, trace endless dependency trees.
It adds up fast.
Yeah. Even if it's being efficient, all of those tool inputs and outputs are being appended to the conversation history. Where does all that data go? Doesn't it eventually clog up the main session anyway?
This is exactly why the architecture introduces plan mode and sub-agent delegation. The exam dictates that for complex, multi-step architectural tasks, the agent should never start modifying code right away. It must enter plan mode.
Plan mode. Okay.
And during this mode, the main agent doesn't actually do the investigating itself. It delegates the heavy lifting to the Explore sub-agent.
Right, I'm going to make sure I'm visualizing this correctly. The main agent essentially acts as the lead architect, and it spins up a separate, smaller instance of itself to act as the junior developer doing the grunt work.
That is a perfect analogy. The main agent instructs the Explore sub-agent, go map out every dependency for this legacy authentication module.
And what's fascinating here is how this physically protects the system's memory. Because that Explore sub-agent operates in its own isolated context window, right?
Completely isolated. All of those verbose file reads, all of those dozens of Grep searches, all the intermediate reasoning where the agent goes down a rabbit hole, realizes it's the wrong file, and turns back. All of that raw token data stays trapped inside the sub-agent's temporary context window.
The main agent doesn't see any of the raw tool outputs.
None of it. When the Explore subagent finally finishes mapping the dependency tree, it synthesizes its findings and returns only a structured summary back to the main session. It hands back an executive report saying, here are the 12 files that need to change, and here is the sequence to change them.
That is amazing.
Yeah, the main agent's context window remains pristine, focused entirely on high-level decision-making and execution.
That is incredibly elegant. It keeps the signal-to-noise ratio absolutely perfect. But that covers internal code-based discovery reading files on the local disk. What happens when the agent needs to understand external systems?
What kind of external systems?
Well, imagine you are building a productivity agent that doesn't just write code, but also interacts with the company's infrastructure.
Yeah.
It needs to know what tickets are in the Jira backlog, or what the schema looks like for the production Postgres database, or what endpoints exist on an internal REST API. How does it discover that information without generating a massive amount of noise?
Ah, you were talking about the discovery overhead problem.
Exactly. If the agent connects to a database, and it has to use tools to figure out what's inside, it might have to call a listables tool, read the output, then call a describable tool for every single table, read those outputs, and try to piece it all together.
It's exhausting.
Right. Making 3 or 4 exploratory tool calls just to figure out what data is available adds massive latency. And again, it eats up the context window with metadata queries before it even starts writing code.
This is where we must introduce the Model Context Protocol, or MCP.
Okay, we've hit the big acronym. What exactly is MCP in the context of this architecture?
Think of MCP as a universal USB plug for AI agents. It is an open standard that allows an agent to connect securely to external data sources and systems. When you connect an agent to an MCP server, say a Postgres MCP server or a Jira MCP server, that server can provide the agent with 2 distinct things, tools and resources.
Okay, I understand tools. A tool is an action, like execute call query or create a Jira ticket.
Correct. Tools are active functions. But the exam guide provides a very specific solution for the discovery overhead problem, exposing content catalogs as MCP resources.
How does a resource differ from a tool?
A resource is designed to expose data structurally at the exact moment the agent connects to the server. Instead of giving the agent a tool called getDatabaseSchema and forcing it to spend time and tokens interrogating the server to guess what tables exist, the MCP server simply exposes the entire database schema as a resource right when the agent boots up.
So what does this all mean? It means tools are actions the agent takes, but resources are maps the agent is handed the moment it walks through the door.
Precisely. By exposing API documentations, issue lists, or database schemas as resources, the agent has immediate, zero latency visibility into the external system. It skips the entire interrogation phase. This distinction between tools and resources is a fundamental architectural principle in the exam for optimizing startup time and protecting the context budget.
That makes total sense. It's the difference between asking for directions at every intersection versus just being handed a GPS. Okay, so now we understand how powerful MCP servers are. They act as the bridge between the agent and the rest of the company's infrastructure. But that raises a massive operational question.
Which is?
Well, if I have a team of 50 engineers, how do I securely distribute these MCP server configurations so everyone's agent has access to the same systems?
This brings us to the strict configuration scoping defined in the syllabus. To manage this at scale, you have to understand the architectural boundary between project-scoped and user-scoped configurations.
Let's start with project scoped. If I want my whole team to have the same Jira integration, where does that go?
Project-scoped configurations live in a file called .mcp.json, and it sits at the absolute root of your project directory. This file is specifically designed to be shared via version control. You commit it to Git.
Okay.
This ensures that the moment a new engineer clones the repository, their local agent immediately boots up with the exact same shared team tools and external integrations.
This raises an important question, though. If .mcp.json is committed to Git and configures our GitHub or Jira MCP server, how do we stop developers from accidentally leaking their personal API tokens or database passwords into the repository? I can easily see someone pasting their production access token into that JSON file and pushing it to main.
That is a critical security vulnerability, and the exam explicitly tests your knowledge of how to prevent it. You must never hardcode credentials directly into the .mcp.json file. The architecture requires the use of environment variable substitution.
So how does that actually look in the file?
Inside the .mcp.json file, instead of pasting your actual token, you use a variable syntax. $sign followed by curly braces containing the variable name. For example, $curly brace GTUD token or Giraffe key.
Ah, I get it. The file just contains a placeholder?
Exactly. When the developer's agent starts up, the MCP client parses that JSON file, sees the placeholder, and automatically injects the actual credential dynamically by reading the developer's local machine environment variables at runtime.
That is incredibly clean. The .mcp.json file itself remains completely free of secrets and perfectly safe to commit to version control. The whole team stays synced, but the security posture isn't compromised. Okay, so that is project scoped. What about user scoped configurations?
User scope configurations live in a completely different place, a file called .claude.json located in the developer's home directory. This file is strictly for personal individual tools. It is never committed to version control.
So for custom stuff.
Right. If a developer builds a custom script to automate their specific timesheet, or if they are just experimenting with a new MCP server locally, it goes in their user scoped file.
And when the agent boots up, it reads both files.
Yes. The agent discovers tools from all configured MCP servers, both project and user scoped simultaneously at connection time. They all merge into the agent's available toolkit.
Which brings up a strategic question regarding how teams should actually build these tools. When should a team build a custom MCP server from scratch versus just downloading an existing one?
The exam has a very clear, pragmatic directive for this. Always choose standard community MCP servers for common integrations.
So if I want to connect the agent to standard SaaS platforms like Jira, GitHub, Slack, Postgres, Gorder, I shouldn't let my engineers waste 3 weeks writing a custom Python server to wrap those APIs.
Absolutely not. Rebuilding standard integrations is a massive waste of engineering time, and it introduces unnecessary technical debt and maintenance overhead. The community servers are already optimized for the Model Context Protocol. The syllabus emphasizes that custom, bespoke MCP servers should be strictly reserved for highly specific internal team workflows.
Like connecting to a proprietary in-house deployment system that no one else in the world uses.
Exactly. You build custom servers for your unique intellectual property, and you leverage the community for commodity integrations.
Here's where it gets really interesting. If we step back and look at everything we've unpacked today, from the absolute strictness of the built-in tool hierarchy, to the mathematical precision of the edit fallback algorithm, to the explore subagent's isolated memory, to exposing data through MCP resources, it becomes incredibly clear what Scenario 4 is actually teaching us.
It is teaching you that an autonomous agent is only as intelligent as the constraints you place around it.
Yes. Developer productivity with Claude isn't just about giving the AI a massive prompt and letting it write code. It is a masterclass in risk mitigation. Every single architectural decision we covered today is explicitly designed to protect the context window and prevent catastrophic file system errors.
Precisely.
Preferring Grep over a glob and weed loop prevents reading irrelevant files. The explore subagent prevents the main session from choking on discovery data. MCP resources prevent expensive, token-heavy interrogation loops.
Which leaves us with a final, rather provocative thought to ponder.
Oh, lay it on me.
We have spent this entire deep dive discussing how to constrain the agent using tools and configuration files like .mcp.json. We've built the walls. But remember, the agent has access to the right tool. It can modify files on the system.
Oh, wow. I think I see where you're going with this.
If an agent is granted the ability to use the right tool to modify its own configuration files based on the incremental investigations it performs, could the agent dynamically alter its own operational constraints and tool access mid-session?
That is wild to think about. An agent reading a code base, realizing it needs access to a different database, writing the connection string into its own .mcp.json file, and essentially recalibrating its own capabilities on the fly. It's the ultimate expression of an adaptive self-modifying system.
It is. But building a self-modifying system safely requires absolute, uncompromising mastery of the foundational constraints we discussed today. Because if you don't enforce the tool hierarchy first, that adaptive system will destroy your project in seconds.
And mastering those constraints is exactly what you need to succeed as a Claude certified architect. Thank you for joining us on this deep dive into the architecture of developer productivity. We encourage you, the listener, to take these strict exam guide principles, the tool hierarchies, the subagents, the MCP resource mappings, and apply them to your own agentic builds. Keep experimenting, keep protecting that context window, and we will catch you on the next deep dive.